So that's the outline of my talk. So the first part will cover the trend and the challenge in AI for network. So for the second part, we will introduce the data knowledge graph-based native AI to meet the requirements of green and real-time needs of the 6G network. The third part will give the network digital twin solution in order to overcome the unpredictable performance of AI use in the 6G network. And we start from the ITU's 6G vision. I think most of people here is quite familiar for this ITU's vision. So because of the time limitation, I don't want to go to the details. So what I should emphasize here is sustainability here, yes, and ubiquitous intelligence. So the sustainability means at least the low cost, low power consumption. However, when talk about the ubiquitous intelligence, which means we need more AI inside the network, which means more computing power. So these two requirements are just a contradiction. Okay, so this is our own view on the 6G in the future. So we call it the 3 beyond. So firstly, beyond the connectivity. So we know for the future 6G, the 6G network will not only provide with wireless communication service, but also with sensing service and AI service in the network age. So to the end of use at a closest distance. So there are two aspects for the integrated AI and the 6G. So that's AI for 6G network or 6G network for AI. By using the AI for 6G, so we can realize autonomous driving and the customized service for the 6G network. By exploring the 6G network for AI, so we can support the deployment of the general large AI models via cloud, edge, and cooperation. But in my talk, I will focus on the AI for 6G network, the first topic. And we just recall the roadmap for the last decade for the AI. So we started from AlexNet to the Sora, to the ChatGPT, to the Sora. And here we show the training computing, the need of the training computing and the data science. So as we can see here, so there is exponentially growth in the data size and the training computing power. So this will be a very big challenge if we implement the AI inside the 6G network. So now, next, so we will summarize some main challenge. The first challenge is a green requirement. So our government just made some commitments. The gas emission needs to be cut in half by the year 2030. So this is a very critical challenge for the 6G development. And we know, so as the network AI improves the performance at the cost of extra computation, so the development of green AI will be very, especially critical. So here we show that in common sense, for the for the AI use in the 6G network, we need the big data, which means big computing and very high energy consumption. If we're not very smart enough, so the power required the energy consumption will be very, very large. But according to the ITU's requirements, the system capacity should be increased by at least 1 magnitude. And meanwhile, if we remain the power consumption unchanged, the bit power consumption should be reduced by at least 1 magnitude. So this is a very big challenge for the 6G development in the future. So the next big challenge is real-time requirements. So we know direct embedding of the AI usually involved massive wireless data and a very heavyweight AI model. So in this situation, so it will be very difficult to make the system real-time. So we should get some very efficient way to efficiently use the data and the efficient model. So only use that way we can make the system real-time. And the third challenge is unpredictability of AI use in the 6G network. So as we know, the AI usually is not explainable and unpredictable. So up to now, even for the large language model, nobody can guarantee the AI work very correctly. So direct deployment of AI algorithms in physical network will be possibly resulting in the unstable network performance. So we should find some proper solution to cope with a very critical challenge. So how to safely use the AI in the network to guarantee the stable network. That's also the big challenge. Okay, so we proceed to the second part, the data knowledge graph-based native AI. So we will see that how to develop a new approach to make the system green and real-time. And here we propose a new framework of the perceived multi-level AI. So actually, this framework consisting of two cycles, the outer cycle and the inner cycle. The outer cycle is non-real-time. So the big data is processed by the data, wireless data knowledge graph to acquire the knowledge of the data. It's working in the non-real-time to acquire the knowledge. So after getting the knowledge, so we form the future data. This data is only necessary for the some system KPI. Not all the data is needed. We only needed some portion of the data for the system optimization. That's the key idea. So after this step, so we will establish some digital twin. That comes later. We will discuss in the third part. So in this way, we make the big data to the small data. So we can use a lightweight AI model. So in this way, so we can make the AI very lower power consumption and can be real-time processed. That's the main idea of our framework. Okay, so this gives some further explanation of how to make the wireless big data to the small samples. So we collect the data from physical communication wireless network. And we analyze the correlation between the different data to establish the data graph. And finally, so we can use it is in real time. So this is a more detailed example here. So the data just analysis by the data graph to get the knowledge. So here, so we evaluate each age weights. We evaluate each data field, the correlation, the relation between the KPI and this data field. And the ranking all these data fields is an influence on the KPI. We only select the most influence, most important data field here. And finally, so we remainder this a small portion of the data. This data is the most important to the system optimization. So this is the main feature. So how to make the larger data set to the small data set. And here is experimental result. So you can see that this is the result here. The performance degradation is not very large. It's a degradation. Yeah, it's acceptable, I think. And but the number of the data field is reduced almost 1 or 2 magnitudes. And the modal parameters and the computational number and the time so can be reduced at least 1 magnitude. So this is our experimental result. So this is some typical example we show here. So for the real-time control of the system. So we finally realize the real-time control of the system. See, we increase the supported UE by 50% with 4K video QoS guarantee. This is a system optimization. It's a real-time. Yes, in millisecond level real-time control. So this is usually very control for the system optimization for the 6G network. Okay, so we move to the third part because the limitation, I think I should speed. So in the third part, so we will discuss how to utilize the network digital twin for the safety use of AI in the 6G network. And here we revisit our framework. So this time we focus on the wireless digital twin part. So we should emphasize that the network digital twin can be served as the replica of the physical 6G network. So by using the network digital twin for the pre-verification, so that it can enable the safety use of AI. Even the AI model is unpredictable and unexplainable. Okay, so here is the chart. So this chart can be more detailed description how the physical network and the digital twin, how they are interacted. So by using the future data set, the digital twin just can hopefully learn the exact behavior of the real network. Then the deep reinforced learning is tried to obtain the policy So the policy is just a trial, pre-verification inside the digital network chain. So after the validation is okay, so the real policy will deploy in the real networks. That's the flow of our digital twin and the system optimization. So here is our example for the RAN slicing optimization. So first, we will use a digital twin to simulate the state. We use a digital twin to simulate the state variation law of the RAN slicing. Then the AI agent try to optimize its performance in digital twin, in the digital twin. So after the re-validation, its performance is okay, so we just deploy in the real environment. And here is a summary result. So as we can see that the performance can be enhanced by really saving can be by the latency. Yes, the air interface latency can be reduced by 38% almost. And finally, so we can see that here, our approach can accelerate the convergence. This is because we only need the interactive between the optimizing agent with the digital twin, not much with the real network. So in this way, so we can reduce the interactive between the time between the AI agent and the real physical network. Okay, that's all for my presentation. Thank you very much.